everyone. So this is part 2 of the GNSS and GPS lecture, and just a recap for week 15's module and what you need to be working on this week is to make sure that you're reading Bolstad chapter 5. You need to participate and complete in discussion 5, which is due May 5th by 11:59 p.m. And then you'll need to be completing Lab 11, and that is actually due on May 12th by 11:59 p.m. And so you have 2 weeks to work on this assignment. And like I said in the last video, I won't be assigning another lab activity next week. So we'll be mostly focusing on review for the final exam and catch up on any assignments that you may have still going. And so at the beginning of next week's module, I'll have the schedule set up for the final and our review sessions. So be looking for that. So tonight, or April 30th at 6:05, the reading quiz for Bolstad chapters 10 and 11 is going to be open, and it'll be open through May 5th, which is this coming Tuesday at 11:59 p.m. Please make sure to take time to take it. You'll have 2 attempts to take the test, the quiz, and it's open book and note, and it'll just be covering those pages that you needed to read for chapters 10 and 11. So please make sure to make the time to take that, because once it's closed on May 5th, you won't have a chance to retake it. Okay, so let's get into the lecture. So at the wrap up of the first part of this lecture, we were talking about different types of GPS receivers or units, and we were talking about the difference between recreational, mapping, and survey grade GPS units. And so let's talk a little bit about the signal really quickly. You might recall that from remote sensing, that passive systems use energy generated by the sun and reflected off of target objects, and active systems generate an energy signal and detect energy return. So you might assume that a GPS signal is going to be an active system, but it's not actually. It's a passive system. It might be a little bit confusing, but the reason why it's considered passive is because only the satellites transmit the signal, and that unit that you're using is the receiver, and that's why it's called a GPS receiver. So it's a passive system. It's called passive because only the satellites transmit the signal. The ranges of the signals broadcast from the GPS satellites to the GPS receivers, and this is the microwave portion of the electromagnetic spectrum. And so the users, or the person who has that GPS unit, is again just receiving that microwave. And then this is one reason why we can have millions of GPS receivers without overburdening the system, because it's just traveling one way. Okay, so the Global Positioning System calculates a position on Earth using satellite ranging and space trilateration. Satellite ranging is the method of finding the distance from a satellite to a location on Earth. The exact location of each satellite must be known to calculate these distances. The ground control stations, along with the regular orbital track of the satellites, make this possible. Each satellite broadcasts a radio signal traveling at the speed of light. The time it takes the radio signal to go from a satellite to a GPS receiver is used to measure distance. Measuring the speed of light requires precise atomic clocks. Each GPS satellite is equipped with these atomic clocks, each synchronized with other satellites in what is known as GPS time. Unfortunately, GPS receivers must also help compute the amount of time it takes for the satellite signal to reach the ground. So because it would be too expensive to include an atomic clock in each GPS receiver, there's something called a PRN code, or pseudo random noise code, And this is a repeating radio signal that appears to be randomly distributed noise. GPS receivers internally track the timing of the repeating pattern in the code. When the GPS receiver receives the PRN code from a satellite, it compares the difference in the pattern to measure how long it took the signal to reach the receiver. So we also have space trilateration. This is a method of determining a position on Earth using the distances from satellites. The GPS satellite constellation functions as a control network, similar to survey control points. Ranging from 3 satellites is enough to fix a horizontal position using trilateration. A 4th satellite is required to determine elevation to correct for receiver clock errors as well. Collecting geospatial data using GPS units requires an understanding of the sources of uncertainty and error and the limitations of the global positioning system. So the United States Department of Defense initially developed Navstar for military applications, and as a defense measure, they included intentional degradation and error in the system called selective availability. So basically, at any time, the Department of Defense can introduce this error into the system when they feel it's necessary for military defense. Currently, a new series of satellites without this selective availability feature called GPS2 are in development. So with selective availability no longer an issue, that leaves one with a series of errors called user equivalent range errors, or UERE. And these are sources of error in satellite ranging that contribute to the total error budget. So the sources of GPS error include satellite clock error, orbital error, atmospheric error, receiver clock error, signal masking, and multipath error. So with clock error or satellite clock error, the atomic clock on board GPS satellites have to be extremely accurate, but can still experience a small amount of error over time. The master ground control station accounts for clock error by broadcasting corrections to satellites using standard GPS time, which are then transmitted down to the GPS receivers. So we have orbital error. The non-spherical nature of Earth's gravitational pull can cause satellite orbits to shift over time. This shift in orbit can cause an error called ephemeris bias. As with the atomic clocks, the master of ground control station tracks the exact location of each satellite and broadcasts the corrections. Each satellite, in turn, transmits corrections down to the GPS receivers. So then we have atmospheric error. When GPS signals enter Earth's atmosphere, the signals can experience a slight deflection and delay. The amount of atmospheric error can vary by location, season, and even time of day. Monitoring stations transmit corrections to GPS satellites, which are then passed on to GPS receivers. Since atmospheric conditions can change quickly, one cannot always correct the source of error in real time. It leaves a certain amount of error unaccounted. Signals from satellites close to the horizon pass through more of the atmosphere, increasing this type of error. So on top of the satellite clock error, we also have the receiver clock error, and this relates to the GPS receiver and local environmental conditions. GPS receivers are equipped with inexpensive clocks that are less stable than the atomic GPS satellite clocks. The error introduced by receiver clocks is minimized using the pseudo-random noise code, or the PRN code. So then we have signal masking, which is a source of error introduced by the local environmental conditions, such as canopy cover, tall buildings, or topography. These obstructions can block the signal from one or more satellites, reducing GPS accuracy. So this is something that you definitely have to think about before you go out to collect your GPS waypoints or your data, whatever it may be, you know, you have to think about if you're going to be going and trying to collect waypoints, like let's say within a forest or like a covered canopy area, you're probably not going to get enough satellites that you're going to need, because remember, you need 3 to be able to get that trilateration, and then you need that 4th for elevation to really be as precise as possible. And so any type of cover is going to mask that signal. And then also you can also have a slowed down signal because of cloud cover. Like if it's a really overcast day, which we happen to get a lot here, you might not get the best signal either. So then we have multipath error. Sometimes the GPS radio signal will bounce off these local obstructions before reaching the antenna, causing a multipath error. When this happens, the GPS receiver acquires the same signal from multiple sources or paths. There is no systematic way to correct this type of error. Sometimes the best method is to move away from obstructions to acquire a signal and then use other equipment such as a compass, measuring tape, or an EDM device to measure the distance and direction to the point of interest. So there's one more error that I do want to talk about. The arrangement of satellites in the sky changes hour by hour. The specific positions of satellites overhead can cause a different type of error called geometric dilution of precision, or GDOP. Satellites high in the sky and close together create more significant areas of uncertainty. The best arrangement to minimize the geometric dilution of precision is to have a satellite overhead with 3 other satellites evenly spaced and close to the horizon. One expresses the geometric dilution of precision numerically as a multiplier of user equivalent range errors. So if you only have that one error, it's going to be really precise. Your signal is going to be very clear. So it's perfect, and it does not magnify that user equivalent range error, or UERE. And this is something that is used in military grade applications. And then if you only have 2 to 3, that's still very good. It's excellent, and that's good for civilian survey grade applications. And then mostly what we encounter in the environmental resource management field is that GDOP of between 4 and 6. When I've been out collecting data for my projects, I usually try to get a GDOP of 6, and that's still pretty good. And it's going to give me the amount of accuracy that I need with my signal to be able to collect the points that I need for my projects. And then, of course, if you have 7 or more, that's poor, and it's not recommended for positioning, and you're only going to get rough estimates of your location. And so if you have your GPS unit and you see that GDOP is over 7, then you might need to wait until a different time of day to see if you could get better satellite reception.